Hello. So good afternoon, everyone. We will be starting today's session. Um, so my introduction. Just a second. Yeah. So let me know if my voice echoes. Okay. And I am Sai Shubham, and I am in my PhD second year. I am pursuing my PhD in electrical engineering from IIT Gandhinagar. Okay. So today's topic, we will be covering the topics of week one. Okay. So today we will do some number system conversion. Okay. So the first question is, suppose this is your number in decimal system. Now it is required for you to convert it into binary system base 2. So when you solve the question, you can put your answers in the comment section. Or maybe we can start with a simple question. Okay. So suppose this is your number, which is binary, and you have to convert it into decimal form. Okay. So you already know the trick. Like if any number it is represented in the binary form, suppose if it is in the binary form, if you have to convert it into decimal form, so the trick is that this is your zeroth position, this is your first, second, third, fourth, and fifth. So the conversion will happen like this: a into 2 power 5 plus b into 2 power 4 plus c into 2 power 3 all the way to f into 2 power 0. So this will give you your decimal representation. So can you use the same logic and solve this? Yes, Tejashwini. I actually can't hear you. I think you have raised your hand. So if you have any question, you have to speak. So this is an easy question. So I will give you 2 minutes. Okay. So I think this is simple one. So I'm discussing the solution right now. So it will go like this. So first you need to check the position. I hope this is clear. So we will go to the next question. So you have to convert this in decimal, okay? So what is different as compared to previous question is that here you have this point, okay? The logic is same. Okay, so the answer of previous question is 183. So let me give you all a hint. If this position is 0, then this position goes as -1 and this is -2, and you have to use the same logic and extend it. So one more minute, after that I will discuss the solution. So it goes like this. So this is the answer. There is an interesting observation. If you take a look, then the first question that I gave you was this number, and the second one is this number. So the first answer was 183, and this is 45.75. Okay. So if you look closely, so what has happened is that the decimal point has shifted by two places. So when it shifts by one place, so a division by two happens. So since it has shifted by two places, so basically there is a division by 4. So is the concept clear? In the same way, if you get a number like this, if you add two zeros, so basically you have multiplied 183 by 4. So this is your answer. So shifting by one place, if it is towards left, you multiply by 2. If it is towards right, you divide by 2. Division and multiplication by 2 is happening because the base of the system is 2. Okay, if the base is n, then you left it, if you shift it left, then it will be multiplication by n. If you shift it right, then it is division by n. Okay, so moving on to the next question. This is your number. You have to convert it into a binary base 2. I will give 2 more minutes, then I will discuss the solution. So I am discussing the solution. Okay. So there are a couple of different methods to achieve this. Okay. Um, like this is 1596 and the closest power of 2. So you first subtract the highest power of 2 from the number. So you can easily subtract 1024. Next you have 572. So you can subtract 512 from it. So the next number that you get is 60. Now you cannot subtract any of this: 2, 56, 128 and 64. So the next number that you should go is 32. Now the next number is 16. Next number is 8, because you cannot, yeah, next number is 8. So since you subtracted it by 1024, so you have this. You also subtracted by 512. Then you have 32. Okay. Then you have 16. Then you have 8. Then you have 4. And you could not subtract it from 2 and 1, so it will be 0. So the answer is, okay. So this is a very long cut method, and I think nobody uses this, but uh, you are getting the feel, right? I hope you got this answer. I will show you a different method. So any binary number is represented in the form of like this. What is the answer? Oh, this is the answer. So any number is represented in this form. So now when you divide by 2, so you will get this as your quotient, and your remainder will be E. Okay. So this is your last bit in your binary representation. So what we need to do is that we need to recursively divide by 2 and get the remainder, and that will form our binary representation. So it will go like this. So the number you are, so this is your answer actually, but it is in the reverse order. This is your LSB, least significant bit. This is your most significant bit. Okay, so the answer is like this. So is this clear? This is actually another method. So we will be moving on to the next question if you don't have any doubts. Uh, Hello Bajas. You have mentioned that problems need to be solved regarding single precision and double precision. So can you elaborate? What are you exactly asking? Are you asking about the float point? Okay. I think initially we will cover the basic number system, then we will move to float point. So I will give 2 more minutes. So solution. So it has two parts. This one we have already solved in the previous question. So this part needs to be converted. Okay. So this can be written as like this. Okay. And this is 2 power minus 1. This is 2 power minus 2. No, this is 2 power minus 4. Sorry, minus 3. So minus 1 is there, minus 2 is missing, minus 3 is also there, minus 4 is also there. So it will be 0.1011. Okay. So we will go to the next question. So the answer is this. Let's try this one. You can answer up to 6 places decimal. I will discuss the solution in 2 minutes. Since we want position up to 6 decimal places, so I have considered the power of 2 up to -6, because beyond that it won't be contributing to the answer anyways. Okay, so first you have 0.5, so this is fine. Next, you cannot add 0.25 because the next result will be 0.75, which is greater than 0.7. Okay, so we have to discard this -2. Next, we have uh, -3. So the net sum will be 0.625, which is less than zero point 0.7. So this is accepted. Now, next we have -4. So this makes your sum 0.6875, which is less than zero point 0.7. So it works. Next, you have -5. So this makes it 71875, which is greater than zero point 0.7. So you have to discard it. Okay. Then next you have -6. So this makes it, we will continue from here because we have discarded it. So we will continue from here. So this is also greater than 0.3125, I think, something like this. Okay, which is greater than zero point 0.7. So we cannot have this. Okay, so this is a non-terminating representation, which means that 4.7 cannot be completely represented in binary form. So that's why I have told up to 6 decimal places, because otherwise the representation is infinite. For example, take a number such as 1 by 3. Okay, so the decimal representation will be 0.333, and it goes on. Okay, so it's the flaw in the system in decimal representation that it cannot be represented in finite number of digits. Okay, so in the same way, it is a flaw uh, in the binary representation system that 4.7 cannot be represented in a fixed number of digits. Okay, so here your answer shall be 100. This comes from here. Point 1 1. One second. So this is your answer. Is this clear? Uh, you had the contribution from point 0.5, so it takes 1. You had no contribution from 0.25, so it will be 0. You had contribution from these two, so 1 1, and no contribution from the following two. Okay, so this is how you convert. Yeah, but the catch is that when you convert this number back to decimal system, so it won't be exactly equal to 4.7. Okay, so there will be some error associated with it. So this is a precise problem in our modern computing systems, that the conversions are not exactly equal. Sometimes it has some loss. Okay, like if you convert zero point 0.7 from decimal to binary, and then you will convert from binary to decimal, then these two values will not be the same. Okay, they are not the same. So in order to minimize the error, what you can do is that you can increase the number of digits into consideration after the decimal point. Okay, so more digits you have, closer it will be to your decimal representation. Does that make sense? So moving on to the next question, we will now focus on conversion from binary, hexadecimal, octal. Okay, so we will have the same problem. This is in your decimal system, and you have to convert it into hexadecimal system. I will be giving you 5 minutes. Okay. Um, I hope you all are familiar with the represent notations. After 9, it will be A, B, C, D, E, and F. So these are basically replacement for 10, 11, 12, 13, 14, and 15. So I will be back in 5 minutes. So I would like to add something. Like previously, as I told you, like 4.7 cannot be exactly represented in fixed number of bits. So this sometimes would lead to some interesting problems. If you remember, about 10 years ago, we would have some old kind of calculators, and there when you perform some simple calculation, suppose if you would perform 0 point many zeros and 2 multiplied by many zeros 2, so it will actually give you 0 as an answer. The problem with that is that it had a very limited number of bits which it can use for the calculation, and this number when converted into binary, it could not be fit in those limited bits. Another interesting thing is that sometimes this error also used to happen in those old calculators. Like if you add 2 plus 2, so it won't give you 4. Instead, it will give you 3.999 like this. So it was because of this issue actually, the problem of representing numbers. So coming back here, right now I will be discussing the solution. Okay. So why did I first check the powers of 16? Because your representation will be in the form of a into 16 power 3 plus b into 16 power 2, like this. Okay. So 16 power 3 is not possible because 4096 is clearly quite greater than 1596. Okay. So the next smaller power of 16 we have to go, which is 256. Now we will divide 256 from 1596, and since we cannot divide 60 anymore from 256, so we will divide 60 from 16. Now, this 12 cannot be divided from 16 anymore, but it can be divided from 1. Okay, so your answer is 6. This is 6, this is 3, and this is 12. But 12 cannot be represented directly. Its representation is C. Okay, so it will be 6, 3, C. This is your answer. Okay, there are other methods as well, like you can do repeated division like this. First, you divide 1596 from 16, so it will be okay. So is your this 12 is your least significant bit. Uh, I think you're aware about least significant bit or most significant bit. For example, I'm representing a 5-digit number. Okay, so this is my least significant position. This is my most significant position. Okay, so the reason behind naming it as most significant and least significant is that suppose my number is 1000 15932 something. Okay, so if I have any error in this position, which is your least significant position, suppose instead of 2 it becomes 3 due to error, so the overall value is still very close. Okay, whether it is 15932 or 15933, it's still the same. But if you have any error in the most significant position, suppose instead of 1 it becomes 5 due to error, so the new value becomes 55932. Okay, which is very much different, which is actually quite bigger than your original value. So this position is most significant as compared to your value, and this is your least significant, because error, when it appears here, has less consequence towards your overall value. Okay, so sometimes when I refer as ls, least significant position, it means the rightmost position. Fine. So this will be represented as C. Okay, now we have got 99, so we will again perform division. So we got 3, and this is 6. Fine. So your answer is 6, 3, C. 6, 3, and C. Okay. So this is another method. I hope this is clear. And I have one another method as well. Okay. So this is your method 1. This is your method 2. Hmm, fine. So you have okay, fine. I will discuss the other method later. Let's move on to the next question. Yeah. So same problem. You have to convert it into hexadecimal. Okay. Take 5 minutes. I think it will be difficult for you right now. I think we should start octal. Okay. So this is your number. Convert it into octal. So in octal, we have these many digits. Okay. So your number will be in this format. Okay. I will discuss the solution in next 2 minutes. Okay. Is my voice not audible? Can you please confirm?
Now it's audible.
Okay.
Your voice is not audible.
No, actually, I'm not speaking anything. Uh, okay. Fine. So we can use the previous approach. Okay. 784. We have powers of 8. Since this is clearly larger, we cannot use this. Okay. Now we will divide 784 by 512. See, most of the people would stop at this position because they think that since they have divided it by 8 and this is octal, okay, this is 8, right? Octal. So they think that since they have divided it by 8, so this is the end of your solution, but it's not. You have to, in the end, divide by 1, okay? Because this is 8 power 0 and this is 8 power 1. So we have to always divide it by 1 at the end, okay? So your answer is 1420, okay? You can do this in another method as well, which many people find simple. So, so as you can see that this quotient is getting transferred here. Okay, so your answer is 1420. Okay. Uh, Actually, I'm not taking the session from 6 to 8, so I'm not aware about that. Next, you have this. Okay. So please note that the given representation is in octal, and and the required representation is in hexadecimal. Okay. Yeah, I will share this share this PDF with you all. Okay, and the recording will also be shared. One more minute. After that, I will discuss the solution. Okay. So first, this number is in octal representation, so we have to convert it into decimal. Okay. Or uh, yeah, and then we will have to convert it into hexadecimal. Okay. So this number is, okay. Now uh, we can take the previous route. We can divide 702 by 16. So uh, this is E, this is B, and this is 2. So your answer is 2BE. Everybody got this? I think yes. Okay. So, but the thing is that every time you cannot sit here and convert the number. Okay. Like if you have to convert octal to hexadecimal, so it's not like every time you will convert it to decimal and then you will convert it to hexadecimal. Okay. Um, Efficient way would be to convert this octal into binary first, and then you can convert into hexadecimal. Okay. So how it is that we will see. So next question is, you have to convert 1 to binary. I will give you 2 minutes. It is pretty easy. Fine. So the answer should be hmm. Okay. So I did a very silly mistake. The thing is that here I have represented. Okay. Fuck. Yeah. So here I have represented everything in the decimal system. Okay. But the problem is that the number is in hexadecimal. Sorry, it's in octal. So how you would convert is that first you would convert to decimal. and from decimal to binary. Okay. Now the problem is that you can take a shortcut like this. This is octal, and the digits in octal are okay. So it it will take, if you represent it binary, it will take 3 digits. Okay, 3 bits. Now if you have to represent this, it will still take 3. Okay. So what we can do is that we can take 3 positions for each digit. Fine. So 1 can be represented as 001, 2 can be represented as 010, 7 can be represented as 111, 6 can be represented as 110. Okay. So this is your binary representation. Okay. This is actually a shortcut method. So what we can do is that if you have to convert any number, suppose 12768 to hexadecimal. Okay. So since it was octal, you took 3 positions, right? If it is hexadecimal, you will have to take 4 positions. As you can see, this is 4 ones. So each one of them is taking 4 positions. Okay. So if you have to convert this number 12768 to hexadecimal directly, so what you can do is that first you will convert them into binary, and then you will convert them into hexadecimal. So yeah, so it will be like this. So this binary representation, and now you have to make a group of 4. Okay, and which will start from the rightmost end. So it will be like this. So this is E, this is B, and this is 2. So your answer will be 2B. Okay, so this is the shortcut. So this is your method 3 of conversion, and this is the most convenient method. So I hope you can convert other numbers as well. Like for example, this is your, one second. Suppose this is your number. In octal, and you have to convert it into decimal. So what will be the answer? Meanwhile, you can try something else as well. Like, so what will be the hexadecimal and what will be the octal? Okay. So take 5 minutes and let me know the answer. Regarding the floating point representation and single precision and double precision, I will cover that in the next tutorial, because I think it has not been yet covered in your weekly lectures, at least in week 1. So after this conversion, I think we will discuss basic addition and then signed numbers, negative numbers. That's all for today. So I am discussing the solution right now. Okay. So 265. This is in octal. So since it's an octal, it will take 3 places. Okay. So for 2 it will be 010, for 6 it will be 110, and for 5 101, and for 16 we have to uh, group in the pair. We have to make a group of 4. Okay. So this and this. So it will be 5. This is 11, right? So it will be B. Moving on to the next question. We have this number. So when we are trying to get an octal, we will make a pairing of three, group of three. So yeah, so this is 5, this is 6, this is 5, and this is 4. If you have to make a pairing group of 4, then it will be, this is B, this is 10. So this is A, and this one is 12. So C. So the answer is, okay, cool. So if you are asked this question, if you go back to the previous question, 1596.6875, okay, it's in decimal. If it is asked that what will be the hexadecimal representation, so I think it is simple now how to handle positions after the decimal point. So this one is easy actually. It will be, this was the answer, okay, for binary conversion. So what you can do is that you can start pairing. So the key thing now you have to note that grouping will always start from this point, okay. So if you have to make a group of 4 or group of 3, then you will have to move this way, okay. And so this is your starting point. What I mean to say is that you don't have to start from the rightmost side, okay, so that will give you a wrong answer, okay. So if you have to uh, we will see the solution, okay. So right now, so this is C, this is 3, and this is 6, 3C dot, and this one is um, so this is the answer, okay. Now if I ask like what will be the octal representation, can you quickly answer in 2 minutes? Please keep in mind that the grouping will always start from this point. Okay, he will start this way or this way. I will discuss the solution right now. If you have to convert it into octal, so grouping has to be done of 3. Okay, so there are some missing numbers like this. This is equal to 5. This is equal to 3 actually. 3, 0, 7, 4. This is 5 and 4. Okay, so your answer is 3074.54 in octal. Uh, does anyone have any doubt so far? Next we will go for negative numbers. So I will give a quick recap. If I have to represent some number, so basically 4 bits. Suppose in 4 bits I have to represent a number. Okay, so it shall go like this. If the first bit is reserved for sign to notify that it is negative or positive, then I have only the liberty of 3 bits. Okay, so in these many bits I have to cover all the numbers. So it will go from 000 up to 0111, that is plus 0 to plus 7. So it's basically like this. This is your endpoint. After 7, you get a number 1000, which is actually minus 8. Fine. Then you have minus 7, minus 6, minus 5, minus 3, minus 2, minus 1. Okay. So if the numbering starts from all 40, then it will be 0001, like this. And after this point, it becomes a negative number. Okay, from plus to minus 8. Then it will keep on increasing. So before 0, minus 1 is always represented as triple one. Now the thing is that whenever they ask you a negative number, suppose they're asking what the representation of minus 4. Okay, so minus 4 is in decimal. They're asking in binary. How will you represent it? So this is only possible when you know that in how many bits of representation they are asking. Like minus 4, if this is your sign bit and this is your 4. If you have to convert, this is your plus 4. If you have to convert to minus 4, what you have to do is that you have to invert all bits. So it will be 0, 1, 1. Invert all bits except sign. Okay, and then you have to add 1. So it will be 100. Fine, and then uh, place sign bit. So it will be 1100. So this one is your sign bit. Fine. So this is how you convert. First you will ignore the sign bit. Then you will consider only the rest of the bits. Then you will invert them. Then you will add 1, and then you will place the sign bit. Okay. So this is how you will convert a positive number to negative number. So this is your minus 4, and you can verify this from the wheel that this is the same number. 1100 1100. But the catch is that here we have specified that this is a 4-bit number. Okay, in a 4-bit number we have represented minus 4. If we have to represent minus 4 in 6-bit number, it will be 111100. So in negative representation, all the preceding bits will be filled with 1. Is that clear? So this is the concept. So now can you represent this number? minus 82 in 10 bits, or in 8 bits. So this is your question. Follow this process, like first represent 82 in positive, uh, first represent plus 82, then uh, follow this path and get to the negative 82. It will be easier that way. So let me know in the comments what answer do you get. So I will now discuss the solution. I hope you could do it. So first we will write plus 82, okay, in binary representation form. So it will be 64 plus 16 plus 2. So this is 2 power 6, this is 2 power 4, this is 2 power 1. So it can be represented as 1 0 1 0 0 1 0. Okay, so these are about 7 bits, and we have a sign bit at first. So it will be 0, which represents that it is a positive number. Okay, and now if I need to convert it into negative number, so what I will do, I will take these many bits, I will flip them, basically invert them, then I will add 1. So so this is my overall number, then I have to prefix 1. So my answer is 1 1 1 0 1 0 1 1 1 0. So this is the answer. So this is actually minus 82. All right. So moving on to the next question. Suppose I have to add two numbers. Okay. Suppose I have to add two numbers. Add in binary. So how will I do? So suppose the numbers are 25 plus 11, and I have to add them in binary. Okay. So this I will show you how it is done. So it will be done in the same way. Um, like the representation is, so you have to have, if you need to add two numbers, so it will be like 1 1. So it will be 0 1 plus 0 1 will be 1 0, right? So it will be 0 and there will be a carry. So this will be 0, there will be carry 1. So here you will have 0 and carry, and this will be 1 0. So this is your final output. Okay, which is 36. As you can see that this position is 32, this position is 4. So 32 plus 4 equal to 36. So now if I tell you to subtract 82 from 36, so how will you do? So it will so let me write down the question. 36 minus 82, and you have to perform in binary. So the hint is that you already know what minus 82 is, okay, and you already know what is 36. Fine. So you have to simply add these two numbers. So this is the last question. After that, I will be ending the session. So let me know what is the answer in binary. So I will discuss the solution now. So 36 is 100. Okay. So this is 36, and we are doing it in 8 bits, right? So we will have to add two more zeros. Minus 82 is, so we can perform simple addition as discussed above. So it will be 0 plus 1, 0 plus 1, 1, 0 plus 1, 1 and 1. So this is the answer in binary. So if you have to convert it into decimal, so what you will have to do is that you are aware that the first bit is the sign bit. So you will keep it separate. Rest of the number is this. You will invert the number again. This is a negative number. Okay. You will invert the number 0 1 0 1 1 0 1, and then you will add 1. So it will be 0 1 0 1 1 1 0. Okay. So now this number is 2 4 8 32. So this is 46, and then we have the sign. Okay, so it will be minus 46. So you can also confirm like 36 minus 82 is indeed minus 46. So what we have suggested in the binary representation is still valid. Okay, so that's all for today's session. uh, in the next session, I will discuss some few operations like addition, subtraction, multiplication in binary, and then we will discuss floating point operation. Okay, so I'm stopping the recording. If you have anything to ask, you can feel free to do so.